So is it visible? Hello.
Yes.
Is it visible?
Yes, it is clear. Yes, that's very good. Thank you.
Shall I start?
Yes, you can start, Professor Azizul Hoque. Thank you very much.
So first, I would like to thank the organizer, including Samsuddin, for having me here for sharing my recent work on the divisibility of class numbers of quadratic fields. So before going to the main topic, I would like to give some background history of the same. So here, so we fixed a number field, say k, and inside that number field, we have a nice structure that is called ring of integers. And in fact, inside that ring of integers, we have a nice concept, so-called these fractional ideals. And in case of this, the set of non-zero fractional ideals, we can define a relation. If I and j are two fractional ideals, then they are related to each other if and only if you can find out two non-zero algebraic integers such that the principal ideal generated by A multiplied by I is equal to the same as for B. And one can check that this relation is an equivalence relation. And thus, we can group them into some classes, so-called equivalence classes. And if I collect those classes, those equivalence classes, it forms a group. That group is called the ideal class group. Okay. In fact, it can define in other way. It can define the set of all the fractional ideals quotiented by the group of principal fractional ideals. So that is the class group. And the number of elements in that group is called class number. Okay. And it's a mysterious object, and it's very, very difficult to understand the things inside this object. So what we do here, we look at the structure of the elements or the structure of the group in some particular cases. And to do so, we look at the divisibility of the class number. Okay, so here I fix the field k is equal to q square root of d, and d is not a perfect square. So this is a quadratic field. And this hd, we mean the class number of this one. Okay. So this lecture is mainly motivated by the source principle. So it's a consequence of Sol's principle. It says that this 3 divides the class number of q square root of d. That implies 3 divides the class number of q square root of minus 3. So one is this real quadratic field that that implies the divisibility of the imaginary quadratic fields. Okay. So now this motivates Komatsu to prove this result. Okay. So in fact, he prove that there exist infinitely many distinct D, such that this 3 divides this pair. Okay, so here this 3 divides pair of fields. Okay, so they may be real or maybe imaginary quadratic fields. Okay. Now, this is one more generalization. In case of this 3 divisibility, here he proved this and divisibility. And in fact, in this case, it is on the imaginary quadratic fields. Okay, so this pair is there. So after that, this another variant. This is considered by Izuka. He considered this D and D plus 1 kind of stuff. So he proved that there are infinitely many distinct negative integer D's, such that 3 divides these simultaneous imaginary quadratic fields here. 3 divides the class number of this Q square root of D and Q square root of D plus 1. And in fact, he conjectured this one that for any prime number phi and to any positive integer m, there are infinitely many m plus 1 successive real or imaginary quadratic fields of this form. And the class number of all these fields are divisible by this p. And in fact, one can look at this conjecture for not only for prime, but for any integer. And if you consider this p is equal to 2, then this conjecture is true by Gauss so-called this. Okay. So this p is for p is equal to 2. This is true by in the sense of Gauss that one. Now, recently, this Chattopadhyay, he's there in the participant, I think, and one of his collaborator, Muthu Krishnan, they consider the result of Izuka, that D and D plus 1, and they were able to add one more field, this Q square root of D plus K square. And here this only 3 divisibility is there. And this result is very, very similar to this Izuka's result. And you can see this some restrictions are there on this K. So here you have this simultaneous thing is there, and one more extra field is there. And it says that this result is true for m is equal to 1. Yeah, so m is equal to 1, and this p is equal to 3. Okay, this is partial. And then this Muthu Krishnan, Krishnamurthy and Poshupulati, they studied this conjecture for any odd this m is equal to 1 and any odd integer. Not only be this p, this any odd integer. Okay. Now, what we look at, we consider the similar problem, but in place of prime, we consider any odd integer n, and in place of this m, we consider a prime number p. Okay. Then we prove that there are infinitely many quadruples of this field. So you have this D plus 1, and D plus 4, and one more field is this D plus 4p square. And we prove that the class number of all these fields are divisible by this n. Okay. And okay, now in my case, in our case, this D is fixed. Okay, so you can construct this all the fields. Okay, so D is of this form. Okay, so K is any positive integer with bigger than or equal to 2. Okay, Now, this extent the result of Izuka and Chattopadhyay and Muthukrishnan, as well as this Krishnamurti and Pashupulati in two directions, one from these pairs to quadruples of fields. And the second direction is that odd, so primes to odd integer. Okay. And this gives a proof of a weaker version in the sense that this n is equal to 1 and okay, so n is equal to 1. So only for one pair it gives a proof of this Izuka's result. Okay. Now to prove this result, we need to prove one more result. This is about the divisibility of these fields. This q square root of p square minus l raised to n with some restrictions. Okay. And in fact, this is an extension of our previous result. And in this paper, we consider the similar discriminant, but the restriction is that in that paper, there was a restriction that L to be an odd prime. But here, we remove that restriction. This L to be an odd prime, we don't need any odd prime, okay? So in case, if we look at this L is any odd prime, in that case, we can't prove this result, okay? So we need to remove that primality condition, and that is why we prove this result, okay? And there is this proof is different from our earlier result, and in fact in the earlier result we use different techniques, but here we prove using binary quadratic the form class groups. Okay. Okay. So if you consider this p is equal to this p prime, p is equal to 3 and 5, then we don't need all these conditions. Okay, so we don't need all the conditions on this p and the other stuffs. Okay, and thus we can look at not only for quadruples, we can look at these quintuples of fields. Okay, okay. Now how we prove this result? This one. I'll give the outline of the proof for this one. So here we do one thing. We connect the class number of the of quadratic fields with form class groups. Okay, so we have a similar structure in the binary quadratic forms with discriminant minus 4d. Okay, so if I consider this d is congruous to 2 mod 4, in that case they are equal. Okay, so then what we do, we use one more result. This is by Huberger and Lee. They proved this. Okay, so this result is connected with this Diophantine equation, so-called Ramanujan-Nagal type equation. So here they consider this kind of equations, and if this equation has a solution, then all other solutions can be written like this. Okay, can be written like this. So this is a unity, and here this exponent, the z, is equal to s into t, and this s and this a and b satisfies these conditions, and this guy divides the class number of this one. Okay, so this guy divides the form class number. So in fact, so we can say that this S divides the class number of the imaginary quadratic field. So what do we need to prove? We need to show that this T must be equal to 1. So if we show that this T must be equal to 1, then this guy will divide the class number. Okay. So in our case, the discriminant is p power p square minus l raised to n. So and d is the square part. So we can write down this p square minus l raised to n is equal to minus d r square. Okay. And from there, we can write down this one. And now we compare this one with this equation. Okay, so then we can say that this P, R, and this N is a solution of this equation, and thus the other solution can be written like this. And this exponent is nothing but this S into T. Now, if we so this must be a star here. This is a star, or you can say that this H of minus D. Okay, now here this S divides the class number. Now we need to show that this S and T N must be equal. So in fact, this if we can show that this T must be equal to 1, then we are done. Okay. Now to show that this T must be equal to 1, we use the technique by Bilu, Handrate, and Hotier. So here we use this Lamar pair. So I start with a pair of algebraic integer such that square of the sum and the product of them are rational integer, and they are co-prime. And this alpha over beta, this should not be a unity. Okay. Then we can define this Lamar number or Lamar sequence like this. L raised to, okay, so like this. If this n is odd, if n is odd, then we can define like this. If n is even, then it is like this. Sorry. Okay, so we have the concept of this Lamar number, and a divisor, a prime divisor of this number is said to be primitive if P does not divide this guy as well as the previous numbers. Okay, so up to n minus 1. Then we say that it is a primitive divisor. Then there is a nice result by Bilu, Handrate, Bautier. They identified all the primitive divisors of Lamar sequence in these two papers. And by using those classifications, we can remove all the odd things. And finally, we can prove that this T is equal to 1. So the proof is very quite lengthy. And thus if T, okay, so we can show that this T is equal to 1. So T is equal to 1 means that n, that exponent is nothing but n. So n divides the class number. Okay. So this is all about the proof of the second result. Now I'll go to the proof of the first result. That okay. So here we define this set. Okay. So for a fixed and odd integer n, and define the set this k is in natural number such that this n divides the class number of q square root of 1 minus this field. Okay. Then we use this result by Lobotin. For odd integer, this n divides the class number of q square root of 1 minus 4 into a raised to n. And in fact, one can prove that there are infinitely many such fields. The infinity is not mentioned in this paper, but one can easily prove that there are infinitely many such fields using Ziegel's results on affine curves. Okay. Okay. Now, since this family has infinitely many such fields, so we can say that this set is infinite set. Okay. Okay. Now this set is infinite. Now we define our discriminant, the D. Okay. So D is nothing but this, okay, so this one. And this is nothing but this, okay, so q square root of d is nothing but this q square root of 1 minus 4 into k raised to n, okay? So those two fields are equal, and thus n divides this h of d. Okay, so for infinitely many negative integers, so this negative because this n is odd. Okay, now we define this a like this, and then we use this result. Okay, so if I define this a is equal to this, then we replace here, plug in here, and then we can calculate that one. You can see that this is nothing but this d plus 1. Okay, so this will give you this d plus 1, and by using this one, we can say that this n divides this. Okay, so now I have this d and then d plus 1. Okay, so then we use another result by Kohn. He considered this this n and this b both are odd integers, and they prove that this n divides this one. Okay, so except for these two cases, this one with one exceptions. Now we can look at this this equation. Okay, so this equation has no solutions except these possibilities. Okay. Okay. Now this has no solution except this one. So except this one, the class number of q square root of minus d is divisible by n. So in fact, this says that there are infinitely these kind of stuffs. Okay, there are infinitely this kind of fields. This q square root of 1 minus b raised to n. Now we replace this b. Sorry, this is actually this this is not a, this is b actually. So now we replace this these things like this. Okay, so we replace this this b by this one minus 4 raised to 4 into k raised to n. Okay, so we replace this by this one and then multiply by 4. Okay, so then this gives us this d plus 4. And by using this one, we can say that this n divides this one. Okay, so we have these three fields, triples of fields are there. Now, finally, I use our second result that L, we replace this L is by this 4 into k raised to n minus 1. And then by using our second result, we can show that this n divides sorry, this n divides this one. Okay. So this completes the result. I have this d plus 1, d plus 4, and d plus 4 into p raised to n. Okay. Now I will stop by after giving this concluding remarks. So here. Okay, so here what we do, we fixed a positive integer m, and pm is denote the largest prime number less than or equal to that p, that m, and this pi m is the prime counting functions. Then our construction that gives this pi m plus 2 number tuples of imaginary quadratic fields of this form. So d plus 1, d plus 4, d plus 36, and like this. And with this divisibility property. Okay. Okay. So very recently, we prove this one more, we construct one more families like this D plus 1, D plus 4, D plus 16, and like this D plus this 4 raised to T. Okay, so here we have this kind of families are there, and with the divisibility property. Okay, now there is a nice result by Beta Kala and their group and his group. The proof a result in case of real quadratic field, but it is not about the divisibility. It is about the consecutive thing is there with large class numbers. Okay, so they prove that there are this kind of this many fields up to x, discriminant up to x, such that the class numbers are constant times of this one. Okay, so bigger than the constant times of this one. So what does it mean? It means that can vary this t is equal to 1, 2, 3 up to k. Okay, so there are these k consecutive real quadratic fields with large class numbers. Okay, so this appears in IMRN. This is a very recent result. But there is nothing is there about the divisibility of the class numbers of consecutive things in case of real quadratic fields. I don't know about if there is if there are some results. I don't know about that, but I think there are no such result because of real quadratic fields. Okay. Okay. So this is all about I have to say. So I stop here. Okay. So thank you. So is there any questions or?
Thank you very much. Thank you very much, Professor Azizul Hoque. So Professor Azizul Hoque is from Harish Chandra Research Institute from Allahabad, India. And we would like to thank him for this very interesting talk. His talk now is open for questions, for discussions. If there is any question from you. Anyone who has a question, he can reactivate his microphone, and welcome. Maybe I have a natural question. For the prime number p, which divides this family of quadratic, which divides the class number of this family of quadratic fields.
Yes.
I'm wondering whether there is any information about the power, the exponent of the prime number p, which divides all these quadratic number fields. Do you have any idea, or is there any research?
See, my result, our result is about any odd integer, right? So this prime power is already there.
We cannot hear you, Professor.
So am I audible? I think so.
Yes, now it's good.
Yeah. So this our result is about this n divisibility, that n is odd prime. Sorry, n is odd integer. This is not prime.
Can you repeat, please?
Yeah. So it is about this odd integer. So this prime power divisibility is already there.
Yes, my question concerning the power or the exponent of this prime, which divides all the class number of this quadratic fields. Can you please return to theorem H, the main theorem of your presentation? I think.
Yeah. Which one?
Theorem H. This one. Yeah. This one. I'm wondering whether here we have the class number of this family of quadratic fields is divisible by P, right?
Yes.
So is there any information about the power of P which divides the class number?
So I'm saying that this one can replace this P by any integer. Okay, so this is a conjecture just. And now if you look at this result,
yeah.
Okay, so this n is any odd integer on any odd integer.
Mm-hmm.
So prime power is already there. So is it clear? So
sorry, give me a second, please.
This is not about prime. Okay, this n divisibility is there. So are you thinking about this rank kind of stuff? P part kind of stuff?
The prime P divides the class number for any positive integer, any prime. There are infinitely many quadratic primes with class number are divisible by n. Sorry. Okay. Yeah. I just understood this. Okay. I thought that the class, the number P divides the class number of these
Okay. Yeah.
Okay, that's good. Thank you very much. Any other questions, please? If you can't say them, you can write them. If you have any question, you can write them in discussions. Okay, so we thank Professor Azizul Hoque for another time and for giving this very interesting talk. Thank you very much, Professor Azizul Hoque.
Sure. Thank you.
And thank you very much. Thank you. And we shall pass to the talk of Katharina Müller from Laval University.
Okay, so I stop here. Yeah.
Thank you very much.